Find the slenderness parameter lambda c. In this problem, a 12-foot long I-beam is subjected to a compression load P. Note that the beam is supported halfway along its length in one direction. A cross-section of the beam is provided, and we notice the end connections are fixed. The modulus of elasticity and yield stress of the steel are also given. Keep in mind, there is only one beam in this problem viewed from two different directions. The slenderness parameter, lambda c, equals KL over R times pi multiplied by root Fy over E. In this equation, we already know the yield stress of the steel, Fy, and the modulus of elasticity, E. If we simplify this equation, lambda c equals 0.01448 times KL over R. In this equation, K represents the effective length factor, L refers to the length, and R is the radius of gyration. Since the I-beam can buckle globally about the x-axis or y-axis, our value for KL over R will be the larger between KL over R in the x direction and KL over R in the y direction. The length in the x direction equals 12 feet or 144 inches. And the effective length factor, Kx, equals 0.65 because of the fixed end connections in the x direction. The y direction is supported at L over 2 with a pin or roller connection. Therefore, Ly equals L over 2 or 72 inches. And a fixed pin end connections have an effective length factor of 0.8. After simplifying these quotients, the last variable we need to solve for is the radii of gyration, Rx and Ry, where the radius of gyration equals the square root of the area moment of inertia divided by the area. Next, we'll return to the given cross-section of the I-beam, A' and increase its size. We'll divide the cross-section into three parts, where parts 1 and 3 refer to the flanges, and part 2 will refer to the web. Now we can calculate the cross-sectional area of the beam, A, by adding the area from each of the three parts. If we add 8 inches squared plus 12 inches squared plus 8 inches squared, the total area equals 28 inches squared. The area moment of inertia, I, is computed about the x-axis and y-axis. If we write out the equation for Ix, we find the area moment of inertia about the x-axis equals 821.4 inches to the fourth power. Next, if we calculate the area moment of inertia about the y-axis, we find the value of Iy equals 86.3 inches to the fourth power. Now we can compute the radii of gyration as 5.416 inches for Rx and 1.756 inches for Ry. Returning to our equation for KL over R equals the larger value between 17.28 and 32.80, which is 32.80. Lastly, we can solve for lambda c by plugging in 32.80 for KL over R, and lambda c equals 0.475. When looking over the possible solutions, the answer is C.